So hello again, welcome back to our video series. And today I'm going to be talking about something I'm going to use C++ to discuss it, and some of the sort of consequences are going to be C++ based, but it is a thing that pretty much, well, largely any language can support. Whether or not they do depends on the language and the circumstances. So the reason this is of particular interest in C++ is it's one of the things where you can get an unexpected outcome in a piece of code, because a C++ compiler doesn't have to compile the code you wrote. It has to produce a program that is equivalent to the code you wrote. And in a few cases, that equivalence is allowed to make certain assumptions, and as long as the outcome is the same, as long as the net result of everything is the same as the code you wrote, that's all that's strictly required. So occasionally this comes up in really hard, really intense optimizations, because a compiler is allowed to, for instance, reorder lines of code, provided the outcome doesn't change by it doing that. And normally, none of it matters, but occasionally in really heavy optimization, if you've accidentally stumbled across, say, some undefined behavior, the outcome can be changed, and that's your fault as a programmer, your problem, but it can lead to really unexpected outcomes. So that is, of course, a reason why undefined behavior is very bad, and why it can have such spectacular consequences, and we'll probably come back to that at some point. We've probably spoken about it before, but today is one specific thing which is actually really to your benefit. And that is the idea that, suppose you have created an object inside a function and you're returning it to the caller. Well, obviously that thing can be created, and it can then be, handed back to the caller, and probably a copy can be made. And that's fine, but you've got a copy. And now, once you're done with that copy, you throw away the object you made, because you keep the copy instead, and that's wholly unnecessary. So there is this idea of, instead of creating a thing, handing it back, making a copy, destroying the original, why not cut out the middleman? Why not create it in the location it's going to be copied into? And that's this idea called return value optimization. You create a thing which is going to be a function return in place in the location it's going to be. And when I say you, I mean the computer here, because this isn't something you do as a programmer, it's something the compiler will do for you. But you do need to be aware of it, because occasionally it gives you unexpected results. So let's knock up a little bit of C++ to demonstrate this. So we're going to need, we're going to need stream.io, because we always need stream.io. And for completeness, let's use the string header. Usually you kind of don't need to do this because it'll have come in through IOStream already, but it's good practice to be clear about your headers, so I'm going to make both of them. And I'm going to create a class so that I can add some custom constructors and destructors that I control, so I can show exactly what's going on here. So I'm going to call my class demo, and everything in it can be public because it's not actually an interesting class. And for purposes, let's give it a single property, which is just going to be a string, and we'll call it name, because that's somehow going to name our class. So we need a constructor to set up that name property. Oh dear, I've got the wrong colon. Constructor from a string in, and it's just going to be name equals in. That's our basic constructor. We don't need a parameterless constructor, because we'll just write the code to make sure we always set up that property. Now, that's a simple class. And now let's write a simple function that's going to return one of these. I'm going to call it fun. That's a very bad thing to do. I shouldn't call it something like that, but this is a demo. It doesn't matter. I can call things whatever I like, because for this purpose, a useful name indicates something about what's being demonstrated, and all that's being demonstrated here is it's a function. Nothing more about it matters. So in this function, I'm going to construct one of those classes. I'm going to use that constructor I just gave, and I'm going to use that to basically indicate where in the program this thing was created by giving it a name property that matches the variable that I'm storing it into. It's some really clumsy kind of manual reflection, but never mind that. And I'm going to return that object. Return my demo. Okay, yep, that's right. And now let's do our main function. And what should we put in there? Well, let's do the obvious thing first. We're going to create another, I've got the wrong quote mark, another of these things. We're going to call it temp this time because it's temporary. And then let's say we want to populate it. Let's say that fun was actually doing something useful and producing some content in that class before it just spits it back. So we're going to do like temp equals, and what that will do is create that temp variable and store into it the result of our function. So far, everything's going to be as expected. We're going to see the creation of a temp variable. We're going to see it we're going to call fun, and that's going to create the my demo, and that's going to return. So in order to actually see this going on, we need to write some actual constructors so that we can see this. So we're going to want, let's do both, because it is occasionally tricky for me to tell whether C++ is going to use copy assignment, which is what I'm writing here, the operator equals, and this is basically given the two entities on the right and left hand sides of that last line of code. This is the constructor that would usually be called to do that equality thing, and the argument to this is a constant entity of our class by convention, because we shouldn't change the thing we're copying from. And inside this function we're going to just tell ourselves, let's see, what should we put? Copy assigning, and let's just indicate where what the input was, so in.name, and end line, oops, daisy, wrong colon again, and that should do. Copy assignment constructor. So let's now have a quick look at what this piece of code does. G++. No return statement. Oh yes, I missed a step in my copy assignment operator. It needs to return the reference. So that needs to return, what does it need to return? Star this, which is a slightly odd idiom, but does come up in things like this because this is a constructor. Right, let's try that. Okay, and run that. And unsurprisingly, we see that a copy assignment is occurring. So I will just quickly write a copy constructor so that I don't get myself in a mess with forgetting how my constructors work. So once again, copy constructor, it's a const input, because you shouldn't change the thing you're copying from, and we'll say in this case copying, and we'll do the same with in.name, and then we should probably actually do the body of the constructor, which in this case is copy, and all we've really got to copy is name equals in.name. So we copy the property, and there we go, one copy constructor. And let's just find out whether creating that changed what happens. Nope, it's still using copy assignment. Not really unexpected, but it is handy. So now let's also create a destructor so that we can see which objects are destroyed, which is a proxy for which objects are ever created. So this time we're going to just go destroying. You learn a lot about your ability to spell things while trying to write code and talk at the same time. And we'll print the name so that we know which entity we're destroying. and end L. There we go, one destructor. So let's see what we've got now. Well, there we go. Pretty much as we expect, that program creates temp, calls function, does the copy assignment from my demo into temp. My demo is then pretty much immediately destroyed, and temp is destroyed when the program ends. And if we want to verify my sort of statement there, let's just put in something here. Oops, I've got caps lock on. That'll do. Nobody cares about correct caps state. And just to verify that my demo is destroyed after that line of code. There we go. My demo is destroyed pretty much immediately after the copy occurs on this line. And then the program ends, and when the program ends, everything is cleaned up, and that leads to the destruction of temp. So far, so as expected. We see that a thing is created and a new one is made. But what if we were to change this code so that effectively temp never needed to be created? So instead of what we have there, we do just this. Now, that code looks rather similar to the previous code, and you might expect that the right-hand side sort of still has to exist, so that the return from fun can be copied into it. You know, if it was an integer, you'd really expect an integer variable to be created, and then whatever's returned from your function to be set as its value. You'd kind of expect this to be the same, at least I would. But here's where the magic happens, which is, hopefully, if we compile that, there is no temp. There's never a temp to be destroyed. There's only ever one object created in that program. And it's destroyed at the end as we'd expect. So basically, this isn't maybe the best example because it's so trivial. But in some sense, no copy assignment is done in that step. There's no need to. Even though, in a sense, you can see where it does need the copy, because temp needs to end up containing the data in my demo. But it doesn't have to do it by a copy if it just does this construct in place. So this is one of those things. Sometimes this just is a surprise because you expect a copy constructor to be called on a line like this, probably something a bit more complicated. You expect the copy constructor to be called, and it isn't, and it can be quite confusing. Why isn't it calling my copy constructor, or why isn't it calling my destructor on, let's see, what would it be? It would be my demo, wouldn't it? And by the way, in the copy assignment, I never actually did the copy, which is why we see the two names being different. Perhaps I should have done that a little differently, but you can get the gist, I think. So, on the whole, well, let's just have a quick look and see if it makes any difference how we do our optimization. Let's deliberately turn off optimization. Nope, so we still don't get a temporary created. What about if we do? Could the compiler perhaps work out, in this case, the two-part case, it can still potentially tell that it doesn't need to create temp, we might think. I don't think it's going to. I think that's a step beyond, but yeah, it's not going to do that. But occasionally the optimization flag can actually change this behavior, and you can end up down a rather confusing route. So just before we go, that's all of the actual code bit, but there's a couple of other things to point out. First of all, this RVO is a special case of what's more generally called copy elision, which is the idea that if a copy can be removed, elided, that is permitted for compilers, C++ compilers, to do in certain circumstances, rather than creating an object and then performing a copy. It's allowed instead to just do the manipulations directly on the target. And of course the compiler has to have enough data to do that, otherwise it couldn't be generating correct code either. But perhaps more importantly, it was actually relied on in my example here, but I forgot to flag it up as we went. This is one of the very, very few things where the C++ compiler is actually allowed to do this, even though it changes side effects. So in the two cases, or in a case where I'd expect a copy to happen, I would expect to be able to add side effects to my copy constructor and reliably see them happening, such as my print statement. But this copy elision is one of the cases where that is just not, the compiler is permitted to assume that just doesn't happen. So even if that constructor has side effects, it can still be omitted. And that's one of the very, very few violations of that thing I started this chat with, which is the idea that the compiler has to produce the same outcome as your code would. Well, in that case, it's not strictly true. It is allowed to change the outcome by omitting those side effects. And that really doesn't come up very often. So this is why this can be such a surprise when you come across it, because you say, but it can't, it's not allowed to change the behavior of my program. Well, in this exact context, it actually is. So that's it.